Hey everyone. In this video, we are going to do another example. We're going to go through this a little bit more quickly than we did the first example and the second example because we're really just doing the same stuff over again. So we have a local school district that claims that the number of school days missed by its teachers due to illness is different than the national average of 5. A random sample of 40 teachers provided the data that we have here below. At the 0.01 significance level, test the district's claim. Then we're going to verify our findings by constructing a 99% confidence interval for our sample. Okay, so the big difference here is we're not given the mean and standard deviation. That's something we're going to have to calculate, but we have the data, so we can easily do that. So first, we're going to create our null and alternative hypotheses. So our null hypothesis is that mean is 5, mu is 5. That's the number of national average of absences due to illness. H sub A, since we just want it to be different, means that we're not equal to 5. So this is a two-tailed test. And so that's going to make things a little bit different as well. And that's all spelled out here. So n is 40 here for the number of teachers, which is larger than 30. So we're dealing with a p-value. And for our two-tailed test, what it says here, and this is always true, is we're going to multiply the calculated probability for a one-tailed test by 2, and that will be our p-value. But first, we need to identify what x bar is, what the mean is, and how did I label that before? Just mu, okay. And then our standard error. Now, x bar I'm not given, but I can find using the average formula. So I'm going to average all of these values, and I get 3.4. Mu is 5, which we already established in our null hypothesis, and the standard error is going to be my standard deviation, STDEV dot S for a sample of these data, divided by the square root of the number of data points, which I can use the count function to figure out how many data points there are. It says 40 here, but I don't always believe what they say. And so that gives me a standard error of 0.3393. Okay, so with this x bar, again, that was the standard deviation divided by the square root of the count. With this x bar is less than the mean. So I'm going to find the probability that x bar is less than 3.4. What's the probability that our mean would actually be this far, our sample mean would be this far from the population mean, the historic population mean? We don't know that this is true. We're saying we are assuming this is true, and then is there a difference between the 3.4 from our staff and the national average? So since this is less than, I can just use regular norm.dist, and I'm going to use x bar, comma, mean, comma, standard error, comma, true. And that comes out to a small number. Now this is the probability that we're less than 3.4, but this isn't the p-value because there's another tail that I have to account for. So I'm going to take 2 times this value, and that will give me my p-value. Now this is a really small number. This is the same thing as 0.0 0.00002411. That's what this value means. Can I write this not in scientific notation? Maybe if I write it, oh, that's not doing it. I don't know how to get this. Oh, that didn't work. There we go. You can see it came out to the same value. So this is significantly smaller than 0.01, which is our significance level. And so we have enough evidence to reject the null hypothesis. And in the context of this problem, there is enough evidence to suggest that the teachers in this district miss a statistically significant amount of different days due to illness than the national average. So we're rejecting the null hypothesis. Now let's construct the confidence interval that goes along with this. This is two-tailed, and again, this is spelled out here. So we have a two-tailed for large samples. So we need to identify alpha, which is going to be the 0.01. We're going to cut that in half, and that will give us the lower tail and the upper tail proportions that we can then use the norm inverse function with. Okay, so I'm going to go through that process right now. We need to know the proportion. We need to know x bar. We need to know the standard error. And this is all for the lower bound. And then we're going to go through the same process. I'm doing this out the long way. You don't have to have all of this information here. As long as you have a cell that you can reference that has the information you need in it, then that's fine. So my proportion down here, since it's a 0.01 significance level, I'm going to take half of that. 0.01 divided by 2 gives me 0.005. That's going to be the proportion in the lower bound. X bar, we already calculated. Standard error, we already calculated. On the upper end, I'm going to take the confidence level, or the confidence level of my confidence interval, that's 99%, and I'm going to add this to it. So 0.99, so as a decimal, my confidence level plus that gives me 0.995. And again, that is spelled out here. It's the confidence level as a decimal plus alpha divided by 2. And then these values are exactly the same. And so now, to find the lower bound, I'm going to use my norm.inverse function. And it's just a straight shot, proportion, comma, mean, comma, standard error. There's my lower bound. My upper bound is going to be norm.inverse, proportion, x bar, standard error, and there's my upper bound. So my confidence interval for this sample is, and I'm just going to do a little trick here where I can join text and values. So I want a space, actually I want a parentheses, then a space, and the lower bound, and I want a comma and a space, and then I want my upper bound. You don't have to know how to do all this fancy stuff. I just like the way that it looks. My confidence interval for this sample is all of this, and we want some end parentheses here, and that should do it. So there's the confidence interval. Now, is the mean, the historic mean, inside this confidence interval? No. Since mu is not in this confidence interval, I should reject the null hypothesis. And so that, again, is just confirming that I should reject the null hypothesis. I constructed a confidence interval, and this mean wasn't in it. And 99% of the time that I do this, it should contain the population mean, which tells me that the population mean is not this. So the population that I'm talking about has a smaller mean, or a different mean in this case. All right. So now, what if these were the only teachers in here? So see this line here, purposely put it here. These are the only teachers. And so now my sample is 28 instead of 40. So it says sample of 40, but what if there's only 28 teachers doing this? Well, again, all of this would be very similar. I'm actually just going to copy and paste it all. My null hypothesis is the same. X bar is going to be different. So X bar is going to be the average, but it's just going to be the average of the first 28 values. And my standard error is going to be different because it's just going to be the standard deviation of the first 28 values divided by the square root of the count of the first 28 values. And so what you'll notice here is that these calculations are no longer valid, because in order to find the probability that we're less than 0.3, in this case 0.332, we need to first find the t-value. So I need to find my t-value, and so t is going to be equal to, this is a small sample, it's less than 30, so I need to find my t-value. Let's remind ourselves what the t-value formula is. Okay, small sample, here it is. T-value, that's going to be X bar minus the mean divided by the standard error, and that gives me negative 4.5233. Now, just looking at this value, I can tell that this is something that is really far away from the mean. It's 4.523 standard deviations away from the mean. So I don't find it likely that the probability is going to be very high here. So I also need to know my degrees of freedom. And that's going to be, we have 28 values now, so that's going to be 27. And so I'm going to use my t.dist function. I need my x, which is actually my t-value, comma, the degrees of freedom, comma, true. And you can see, oh, sorry. We don't take the absolute value when we're doing a regular test. Instead, we only take the absolute value when we're doing a confidence interval. So you can see here that this value isn't, even though it's not as small as this one was, it's still a very small probability. So this is less than the 0.01 that we were looking for. Even after I double it 2 times, need to double it. This is still less than our 0.01 significance level, and so we will reject the null hypothesis. And the reason is exactly the same, so I can actually copy and paste that. There is enough evidence to suggest the teachers in this district miss different amount of days than the national average. So now let's go ahead and find the confidence interval for this. So again, I need to know my proportion, which I already have. I need X bar and standard error just to find the, actually I just need my t.dist, I need my critical number and then my standard error. So I'm going to find my t critical, and that's going to be for the lower bound is going to be t dot inverse, and I'm going to use the probability 0.005 and the degrees of freedom, which is up here 27, and that's going to give me negative 2.77. I am going to take the absolute value of that. So this is t critical, and this will work. This will work over here too. I guess I just wanted to paste the value. Copy, paste value. So that's the same critical value over there. And then to find the lower bound, I'm going to do, I need to find the margin of error. Which has a letter. So that's E. I'm going to take my critical value. I'm going to multiply it by my standard error. So there's my standard error. And then my lower bound is going to be the mean minus my error. And then same thing over here. So I'm going to find E, and that's going to be the critical value times the standard error. It's the same value, but then my upper bound is going to be equal to the mean plus my margin of error, and that gives me 4.34 or 35. And then you can see my data points have moved. But my confidence interval for this sample is from 2.293 to 4.3496. And since mu is not in that confidence interval, mu was 5, then I should reject the null hypothesis. So that's how we go through this process again, just using when we're given a sample. The big difference is we have to calculate X bar using my average formula, and we have to calculate the standard error using standard deviation and other built-in formulas. But the rest of the process is exactly the same. And what we also got to see here was a two-tailed test. In the next video, we're going to do an example that has population proportions, and then we'll be done.